In Chapter 7, we're looking at the idea of a sampling distribution. This is where we're going to start to formalize the idea of statistical inference. Statistical inference is where we take many samples from a population so that we can try to make a conclusion about that population. One thing to remember is that every time you take a sample, you're going to get different results. That's natural. That's called sampling variability. Here's how this process usually works. We take a population that we're interested in. We take a sample from that population, collect data, and look at something like the mean or the proportion of some characteristic that we're interested in. And then we use that data to make a conclusion or to make an inference about the population. Now we need some vocabulary to really be able to talk about these ideas. So first we need to look at the difference between a parameter and a statistic. They're very similar. They're things like means, proportions, standard deviations, but when you're talking about the sample, those are all called statistics. And when you're trying to generalize those things to the population, those are called parameters. One way to help you to remember this is to remember the S and the P. So statistics are about samples, parameters are about populations. Now we use the letter mu, which looks like, this is incorrect here, it looks sort of like a cursive U. We use that for the mean of a population, whereas we use the X bar that we're familiar with as the mean for the sample. Similarly, we use a lowercase p to represent a proportion for a population, and we use p hat, which is the p with the little up arrow looking thing on top of it, for a proportion of a sample. Let's go back to that idea of sampling variability that we mentioned at the beginning of the video. We want to know whether or not, for example, the mean of a sample can accurately represent the parameter for the population, the mu. Since we're going to be getting different means every time we say take a sample, it seems counterintuitive that we can use that to make some conclusion. So that's where sampling variability comes in. We want to know what type of numbers we're going to get, like how spread out are they. So we want to look at what happens if we take many, many samples. So we go to our population and we keep taking sample after sample, and then we put those all together. And when we put them all together, that's what we call a sampling distribution. So if we take every possible combination of sample sizes of size n, n's arbitrary, so maybe you take sample sizes of size 3 or sample sizes of size 5. Whatever it is, you stick with it. So if you're taking a sample of 10 people, you do that every time. And we use that to come up with a sampling distribution. Now, oftentimes we don't actually do a sampling distribution because sometimes there are millions of possible sample sizes of size n. So what we do instead is we'll use simulations. So we'll use your calculator, we'll use the random integer generator, we'll use a computer to make dot plots of many, many samples, even though sometimes it's not possible to get every possible sample. One thing that people often confuse is the difference between a sampling distribution and a population distribution. And actually there's a third distribution as well. So one distribution is the population distribution. That gives a distribution of possible values for some variable for every single person in the population. Whereas if we take a distribution of sample data, that shows one single sample. Maybe we took a sample of size 10 and we put those 10 people or those 10 subjects onto a dot plot. That would be a distribution of sample data. Now, if we take a sample of 10 people and find the average and put that as a dot on the dot plot, and then do another sample of 10 and put that as a dot on the dot plot, and then take another sample of 10 and take that and put that as a dot on the dot plot, and we keep repeating that. That is what we call a sampling distribution. So let's take one more look at these in a visual pattern. let's say that we had candies and we know that exactly half of them are blue and exactly half of them are red. That would represent the bar graph on the left. That is our population distribution. Now in the middle, we've got 3 different samples. Maybe we picked 20 candies at random, and the first time we had 12 blues and 8 reds. And then the second time we had 9 blues and 11 reds. And then the third time we had 7 blues and 13 reds. Each of those is a distribution of sample data. Now, if we take the proportion of reds, for example, in each of those, so the 0.4 for the first one, 0.55 for the second one, 0.65 for the third one, and we do that many, many times and put those as dots on a dot plot on the right-hand side, that becomes our sampling distribution.